Jupiter was never a failure. It was never meant to shine. In the stillness of the solar system, there is a massive presence moving slowly, steadily, and without urgency. It does not glow. It does not burn. It does not announce itself with light or brilliance. Jupiter remains there, a vast body of matter that has chosen silence over spectacle. It has often been called a failed star. But when you listen carefully, that idea begins to lose its meaning. There is no sense of something unfinished here. No regret. No trace of a dream left behind. Only a slow and patient motion, unfolding across spans of time too large to measure with calendars or memory. Layers of thick clouds drift like breath. Great storms endure, not to impress, but simply to continue. Tonight there is no need for excitement, no pursuit of brightness. We are only staying with a quiet truth. Some objects in the universe do not need light to be essential, and Jupiter is one of them. If you are looking for a quiet place to rest for a while, you may subscribe to this channel, so these slow, gentle space stories are always here whenever you need them. To understand what Jupiter is, it helps to begin with what it never was. Jupiter did not emerge from the heart of a collapsing stellar core. It was not born in the same violent way stars come into being. From the very beginning, its path was quieter, slower, and fundamentally different. Jupiter formed inside the protoplanetary disk, a wide, rotating plain of gas and dust that surrounded the young sun. This disk was not a place of explosive collapse, but of gradual gathering. Particles drifted, collided, and settled. Over time, gravity encouraged material to collect in certain regions, not all at once, but patiently. In one of those regions, far from the sun's growing heat, Jupiter began to take shape. The material itself was familiar. Hydrogen and helium dominated the disk, just as they dominate the sun. This shared origin often leads to confusion. If Jupiter and the Sun came from the same cosmic cloud, the same ancient nebula, shouldn't their destinies have been similar? The answer lies not in what they were made of, but in how they came together. The Sun formed through gravitational collapse. A dense region of the nebula pulled inward on itself, growing hotter and denser until nuclear reactions became inevitable. Jupiter never experienced this kind of collapse. There was no single moment where its core imploded under its own weight. Instead, Jupiter grew the way planets do, by accumulation rather than collapse, by addition rather than ignition. Space rarely gives us simple answers. At first, a solid core likely formed, built from rock and ice. This core provided a gravitational anchor, strong enough to attract surrounding gas from the disk. Over time, vast quantities of hydrogen and helium flowed inward, wrapping the growing planet in thick, layered atmospheres. The process was slow, almost gentle by cosmic standards. There was no flash of light, no sudden transformation, just steady growth, unfolding across millions of years. What matters most here is that Jupiter's identity was established early. Long before it reached its immense size, it had already chosen, in a physical sense, the path of a planet. It did not hover at the edge of becoming a star. It did not hesitate between two roles. The conditions required for star formation were never present in its region of the disk. This distinction is subtle but essential. Stars require extreme concentration of mass in a very small volume. Jupiter's mass, impressive as it is, was spread out across a much larger region. The surrounding disk environment favored planetary growth, not stellar collapse. Gravity worked slowly, shaping orbits and layers rather than compressing matter into a blazing core. Silence is also a kind of data. As Jupiter continued to grow, the sun was already shining. This timing matters. By the time Jupiter reached its final mass, the surrounding gas in the disk was thinning, shaped by solar radiation and stellar winds. The opportunity for anything resembling star formation had long passed. Jupiter was completing a process that had always been planetary in nature. From a human perspective, it is tempting to imagine alternative outcomes. We like stories where things almost become something else. Almost a star. Almost a sun. But physics does not work on almost. It follows thresholds, environments, and histories. Jupiter never crossed the thresholds required for stellar birth, not because it fell short, but because it was never approaching them. Numbers whisper more than they speak. Even early in its formation, Jupiter's mass was orders of magnitude below what is needed to trigger nuclear fusion. That gap was not narrow, it was vast. The idea that Jupiter was once close to becoming a star comes more from our narrative instincts than from astrophysical reality. Instead, Jupiter became something else entirely. A gas giant shaped by slow accumulation, layered structure, and internal heat rather than nuclear fire. Its story is not one of failure or missed potential. It is a story of specialization, of taking shape in the right place, under the right conditions, at the right time. When we step back and allow the process to unfold at its natural pace, Jupiter's origin feels less dramatic, but more complete. There is a quiet confidence in a body that never needed to become anything else. No collapse, no ignition, just a steady presence, growing into the role it still plays today. And in that slow beginning, we can already sense a larger pattern forming, one that does not rush toward brightness, but settles into balance, as if the universe itself knew exactly where Jupiter belonged. At first glance, Jupiter seems familiar. Its vast atmosphere is made mostly of hydrogen and helium, the same simple elements that dominate the Sun. This resemblance is often the starting point of confusion. When people hear that Jupiter and the Sun share the same primary ingredients, it feels natural to assume that they share the same story, or at least the same destination. But in the universe, similarity in material does not guarantee similarity in fate. Hydrogen and helium are not rare or special ingredients. They are the most common elements in existence. They filled the early universe long before stars, planets, or galaxies took shape. When we look at Jupiter's composition, we are not seeing something exceptional. We are seeing the default building blocks of almost everything large and gaseous in space. Space rarely gives us simple answers. The Sun is dominated by hydrogen and helium because it formed from a dense region of gas that collapsed inward until nuclear fusion began. Jupiter contains hydrogen and helium because it grew within a disk already rich in those elements. The ingredients are the same. The processes are not. This difference matters more than it first appears. In everyday human experience, materials often define purpose. Steel becomes a bridge, wood becomes a house. We are used to thinking that what something is made of tells us what it is meant to become. In astronomy, that intuition often fails. Many gas giant planets across the galaxy share Jupiter's basic composition. Observations of exoplanets show worlds even larger than Jupiter, wrapped in thick hydrogen and helium atmospheres, orbiting distant stars. Some are hotter, some are colder, some are far more massive. Yet they are all planets, not stars. Because composition alone does not trigger starlight. Silence is also a kind of data. What truly separates stars from planets is not what they contain, but what happens at their cores. Stars ignite because their mass compresses hydrogen to extreme temperatures and pressures. Planets do not. Jupiter's hydrogen remains unlit no matter how familiar it looks to us on a chemical chart. The phrase, "almost a star," often appears in casual explanations, especially when people encounter Jupiter for the first time. It feels comforting, almost poetic. As humans, we like thresholds. We like to imagine Jupiter standing just shy of greatness, paused at the edge of transformation. But this image says more about us than it does about Jupiter. Numbers whisper more than they speak. When we examine the actual physical values involved, the picture becomes clearer. Jupiter's mass is nowhere near the range where star-like behavior begins. The gap is not subtle, it is enormous. The shared elements create a visual and conceptual resemblance. But the physics underneath tells a different story, one that unfolds quietly and without ambiguity. There is also a psychological element at work. Humans are pattern-seeking by nature. We look for continuity, for gradual transitions, for smooth progressions from small to large, dim to bright. Jupiter disrupts that expectation. It looks like it belongs closer to the Sun than it does, at least in composition. That visual closeness invites interpretation and sometimes misinterpretation. In science communication, metaphors are often used to bridge understanding. Calling Jupiter a failed star is one such metaphor. It shortens a complex explanation into a single phrase. It grabs attention, but it also blurs the reality. Jupiter did not fail at becoming a star. It simply followed a different set of physical rules from the start. Many gas giants in other systems demonstrate the same truth. They are rich in hydrogen and helium, yet they orbit calmly, never igniting, never collapsing inward. Their existence reinforces an important lesson. In the universe, destiny is shaped by conditions and processes, not by appearances. As listeners, especially late at night, it can be comforting to slow down and let go of the need for dramatic labels. Jupiter does not need to be almost anything. Its identity is complete as it is. The similarity we notice is real, but its meaning is limited. When we allow that idea to settle, the universe begins to feel less like a stage for near misses and more like a system of precise balances. Familiar materials, unfamiliar outcomes, shared origins, separate paths. And perhaps that quiet distinction is its own kind of clarity. One that does not rush toward conclusions, but rests comfortably in the space between what looks similar and what truly is. When people imagine Jupiter as a near star, they often picture it standing just below a hidden threshold, as if a small addition might have changed everything. But mass in the universe does not work that way. It does not blur at the edges. It does not gently fade from one category into another. Mass draws clear boundaries, and Jupiter has always stood far from the one that separates planets from stars. Jupiter is enormous by planetary standards. It outweighs all the other planets combined. Its gravity shapes orbits, captures moons, and quietly governs large regions of space. Yet compared to the Sun, its mass is small. Jupiter contains only about 0.1% of the Sun's mass. Not 1%, not even close. 1,000 Jupiters would be needed to match the Sun. This difference is not a technical detail. It is the core of the story. Space rarely gives us simple answers. To begin nuclear fusion, the process that defines a star, matter, must be compressed to extreme temperatures and pressures. That compression depends almost entirely on mass. Gravity must be strong enough to squeeze hydrogen atoms until they collide and fuse. Jupiter's gravity, powerful as it feels to us, is nowhere near sufficient to do this. Even the threshold for a brown dwarf, objects often described as halfway between planets and stars, lies far beyond Jupiter's reach. A brown dwarf requires roughly 13 times Jupiter's mass to ignite even the faintest nuclear reactions. This is not a small step upward, it is a leap across a wide and empty gap. Numbers whisper more than they speak. When scientists compare these values, the picture becomes quiet and unmistakable. Jupiter is not just below the boundary, it is comfortably distant from it. There was never a period when Jupiter hovered near the edge of becoming something else. Its growth never approached stellar conditions, even briefly. From a human point of view, it is easy to underestimate how large these differences truly are. Our intuition is shaped by everyday scales, where small additions can produce meaningful change. A few extra pounds alter balance, a few degrees change comfort. But cosmic mass operates on a different logic. Here, factors of 10 matter. Orders of magnitude define reality. Silence is also a kind of data. Throughout its formation, Jupiter accumulated gas until the surrounding disk thinned and the process naturally slowed. There was no runaway collapse, no moment when gravity began pulling inward uncontrollably. The environment simply did not allow it. The available material was limited, and the Sun's growing influence shaped the disk in ways that capped Jupiter's growth long before stellar thresholds became relevant. This is why the phrase "almost a star" feels misleading. It suggests proximity where none existed. Jupiter did not stop just short of ignition. It stopped where planets stop. The difference between a planet and a star is not ambition or effort, it is physics. Jupiter could not have become a star unless the entire structure of the early solar system had been different. The Sun would have needed far more mass, the disk far more material, and Jupiter's region far greater density. Without those conditions, the outcome was never in question. There is a human lesson hidden in this clarity. We often frame outcomes in terms of success and failure, as if everything moves along a single ladder of progress. Bigger, brighter, stronger. But the universe does not organize itself this way. It creates distinct categories, each with its own balance and purpose. Jupiter's mass places it firmly within one of those categories, not as a star that fell short, but as a planet that grew large enough to matter in a different way. Its gravity influences the architecture of the solar system. Its size shapes the distribution of smaller bodies. These roles do not require nuclear fire. If we pause and sit with the numbers long enough, the drama fades. What remains is precision. Jupiter never crossed a boundary because it never approached it. Its history is not one of near misses, but of defined limits. In the quiet language of physics, this is not a story of disappointment. It is a story of placement, of mass settling exactly where it belongs, neither too small to matter nor large enough to burn. And as we drift deeper into that understanding, the universe feels less like a collection of unrealized possibilities and more like a careful arrangement of forms, each complete in its own stillness, resting calmly on the side of the boundary it was always meant to inhabit. At a distance, Jupiter and brown dwarfs can appear related. They are both large, massive, and dominated by hydrogen and helium. To someone encountering these objects for the first time, the distinction may feel subtle, almost semantic. But when we slow down and look carefully at how they come into being, the difference becomes clear and surprisingly quiet. Brown dwarfs are born the way stars are born. They begin inside dense regions of gas within molecular clouds. Gravity pulls matter inward, faster and faster, until the core heats dramatically. This process is not gentle, it is a collapse. A brown dwarf forms from the same kind of inward rush that creates stars, following the same physical script, at least at first. For a brief time, some brown dwarfs even manage to ignite limited nuclear reactions. Not the long-lasting hydrogen fusion that powers stars like the Sun, but weaker reactions involving heavier forms of hydrogen. These reactions do not last. The mass is not sufficient to sustain them. Eventually, the interior cools, the reactions fade, and the object settles into a slow decline. This is why brown dwarfs are sometimes described as failed stars. They begin on a stellar path and do not complete it. Jupiter's story is different from the very beginning. Jupiter did not form from a collapsing cloud core. It grew inside a protoplanetary disk, orbiting a star that already existed. Its growth was shaped by rotation, by orbital motion, and by the availability of material in the disk. There was no inward plunge toward ignition. There was no brief moment of nuclear activity. Jupiter never stepped onto the road that leads to starlight. Space rarely gives us simple answers. This distinction is not just technical, it reflects two fundamentally different processes at work in the universe. Brown dwarfs are objects that try to become stars and fall short. Jupiter is an object that never tried. One path is defined by not enough mass, the other by not needing that mass at all. Numbers whisper more than they speak. When scientists compare the masses involved, the separation becomes unmistakable. Brown dwarfs are many times heavier than Jupiter. Their formation requires a density and gravitational environment that simply did not exist in Jupiter's region of space. Even at its largest, Jupiter remained far below the range where star-like behavior begins. It is tempting, especially from a human perspective, to imagine a smooth continuum. Small planets, larger planets, brown dwarfs, stars. A single ladder of growth. But the universe does not always organize itself along a single line. Sometimes it builds separate roads that never intersect. Silence is also a kind of data. Jupiter's interior tells this story quietly. There are no signatures of past nuclear reactions, no evidence of a stellar phase that flickered and faded. What we see instead is a planet shaped by gravity, pressure, and slow heat release, not by fusion. Its warmth comes from gradual contraction, not from nuclear fire. For listeners late at night, this difference may feel oddly familiar. In our own lives, we often confuse outcomes with intentions. We assume that if two things look similar, they must have wanted the same result. But intention does not exist in physics. Only conditions do. Brown dwarfs exist because certain regions of space were dense enough to collapse, but not dense enough to sustain a star. Jupiter exists because its region allowed planetary growth to proceed efficiently without ever crossing interstellar territory. Each object fits the environment that shaped it. There is a kind of relief in this clarity. Jupiter does not carry the burden of an unfinished transformation. It is not a star that lost its chance. It is a planet that fulfilled its role completely. As we let this distinction settle, the label failed star begins to dissolve. What remains is a quieter understanding. Some objects fall short of a goal they began pursuing. Others never pursue that goal at all. Jupiter belongs firmly in the second category, and perhaps there is something calming in recognizing that not every difference needs to be framed as success or failure. Sometimes it is simply a matter of taking a different path, one that never required fire, never aimed for brilliance, and still arrived exactly where it was meant to be. Moving steadily through space, complete in its own form, without ever needing to become anything else. The phrase failed star did not come from the quiet language of astronomy. It did not emerge from equations, models, or careful observations. Instead, it entered public awareness through storytelling, through simplification, and through a very human desire to make the universe feel familiar. The term began appearing in popular science writing decades ago, especially in books, documentaries, and articles aimed at general audiences. It was never meant to be a strict scientific label. It was a shortcut, a way to explain Jupiter's size and composition in a single, memorable phrase. Large, gaseous, mostly hydrogen and helium, almost like the sun, but not quite. For communication, the phrase worked. It caught attention, it sparked curiosity, it gave people a mental image they could hold on to. In a world where space often feels distant and abstract, calling Jupiter a failed star made it feel closer, more dramatic, more understandable. Space rarely gives us simple answers. The problem is not that the phrase is malicious. It is that it compresses too much meaning into too little space. When people hear failed star, they imagine a process that tried and did not succeed. They imagine something that came close, paused, and stopped just short of becoming what it was meant to be. That story is emotionally intuitive. It is also scientifically inaccurate. Modern astronomy does not classify Jupiter as a failed star. It never has in any formal sense. Jupiter does not meet the criteria for stars, for brown dwarfs, or for any transitional stellar category. Its formation history, mass, and internal processes place it firmly in the category of planets. Numbers whisper more than they speak. So why does the phrase persist? Part of the answer lies in how humans relate to stories. We tend to frame processes as journeys with outcomes, success or failure, arrival or collapse. But nature does not operate on narratives, it operates on conditions. When the conditions for star formation are present, stars form. When they are not, they do not. Jupiter did not fail at becoming a star. It never attempted it. The conditions required for stellar birth were never part of its environment. Calling it a failed star suggests an intention that never existed. Silence is also a kind of data. In scientific literature, the term rarely appears except as a reference to outdated or informal language. Researchers describe Jupiter as a gas giant planet, formed through accretion in a protoplanetary disk. Brown dwarfs are discussed separately, with clear definitions and measurable boundaries. The distinction is not controversial. It is well established. Yet popular language moves more slowly than scientific consensus. Phrases linger because they are familiar, not because they are accurate. Failed star sounds intriguing. Gas giant sounds ordinary. One invites imagination. The other invites patience. There is also an element of scale that misleads us. Jupiter is so much larger than Earth that it feels as if it belongs in a different category entirely. For someone encountering planetary science for the first time, the leap from Earth to Jupiter feels almost as large as the leap from Jupiter to the Sun. The phrase failed star fills that gap with a simple explanation. But simplicity has a cost. When we rely on that phrase, we lose the ability to see Jupiter for what it actually is. We stop asking how it formed, how it works, and why it matters. We replace a complex history with a single label. From a human perspective, this habit is understandable. We do the same thing in daily life. We summarize people, events, and experiences with shorthand descriptions that help us move on. But when we slow down, especially late at night, those shortcuts begin to feel less satisfying. Jupiter does not need a dramatic backstory. Its real story is quieter and more interesting. It is a planet shaped by gradual growth, limited material, and precise physical boundaries. Its size is not evidence of a near miss. It is evidence of how planetary systems naturally organize themselves. As science communication evolves, there is a growing effort to move away from misleading metaphors, not because they are harmful, but because they are incomplete. The universe does not become clearer when we force it into familiar emotional categories. In the end, the phrase failed star tells us more about how humans explain the cosmos than about Jupiter itself. It reflects our preference for stories with tension and resolution. Jupiter offers something different, a reminder that not every object needs to be framed as almost something else. When we let go of the label, Jupiter becomes simpler, not more mysterious. A planet that formed as a planet, a giant, quiet presence that never needed to ignite to have meaning. And perhaps there is calm in recognizing that understanding does not always come from dramatic language, but from allowing things to be exactly what they are, without asking them to carry a story they were never part of. The phrase failed star did not originate in the careful language of modern astronomy. It did not come from peer-reviewed papers or from the quiet confidence of equations. Instead, it emerged from popular science, from a space where explanation meets storytelling, and where complexity is often softened to feel more familiar. In books, television programs, and articles written for general audiences, Jupiter was sometimes described this way to help people grasp its size and composition. A planet larger than all the others combined. An atmosphere dominated by hydrogen and helium. From a distance, these traits felt close enough to the Sun to invite comparison. The phrase failed star offered an easy bridge between what people already knew and what they were trying to imagine. It was never intended to be precise, it was intended to be memorable. Space rarely gives us simple answers. The term persists because it works on a human level. Humans understand stories through contrast, success and failure, arrival and incompletion. Calling Jupiter a failed star suggests a narrative arc, something that almost became something else. A near miss. That kind of framing is emotionally intuitive, even comforting, because it mirrors the way we tell stories about ourselves. But physics does not share our preference for narrative. From a scientific perspective, the phrase introduces a subtle distortion. It implies that Jupiter began the same journey as a star and simply did not make it far enough. That implication is incorrect. Jupiter did not start down the stellar path. It did not attempt fusion. It did not experience a stellar collapse phase. It formed as a planet and remained one throughout its history. Numbers whisper more than they speak. When astronomers classify objects, they rely on measurable properties and formation mechanisms, mass, internal processes, and origin matter far more than appearance. By these measures, Jupiter fits cleanly into the category of gas giant planets. It does not sit near a boundary. It does not occupy a grey zone. The scientific consensus on this point is clear and uncontroversial. So why does the phrase remain in circulation? Part of the answer lies in how information travels. Scientific understanding evolves, but popular language often lags behind. Once a phrase becomes widespread, it tends to repeat itself, passed along because it feels familiar rather than because it is accurate. Over time, repetition can give the impression of authority, even when the underlying idea has been left behind by science. Silence is also a kind of data. Another reason the phrase endures is that it satisfies curiosity quickly. It offers an answer without demanding patience. Calling Jupiter a failed star seems to explain its size in a single step. But that convenience comes at a cost. It closes the door on deeper questions about planetary formation, disk dynamics, and the role of environment in shaping outcomes. Modern astronomy avoids the term precisely for this reason. Researchers describe Jupiter in terms of what it is, not what it is not. A gas giant formed through accretion in a protoplanetary disk, an object with internal heat generated by slow contraction. A planet whose influence comes from gravity, not from light. When we slow down and listen carefully, the absence of the phrase in scientific work becomes meaningful. It tells us that the label no longer serves understanding. It belongs to an earlier stage of explanation, one that favored metaphor over mechanism. There is something deeply human about this progression. We begin with stories because stories are accessible. Over time, as understanding grows, those stories are refined or set aside. Not because they were wrong in spirit, but because they are no longer needed. For a listener late at night, this realization can feel grounding. Jupiter does not carry the weight of a failed attempt. It does not exist in the shadow of what it could have been. It exists exactly as it formed, shaped by conditions that were sufficient, complete, and stable. The phrase failed star says more about how humans once tried to make sense of Jupiter than it does about Jupiter itself. It reflects our habit of explaining the unfamiliar by comparing it to the familiar, even when that comparison bends the truth. When we release the label, something quieter takes its place. Jupiter becomes easier to understand, not harder. A planet with its own origin, its own role, and its own balance. And perhaps that is enough. In a universe that does not rush toward meaning, clarity often arrives not through dramatic names, but through the simple act of letting objects be what they are, without asking them to fit a story they were never part of. The phrase failed star did not emerge from careful measurement or from the slow confidence of scientific consensus. It came from somewhere much closer to everyday human experience. It came from popular science, from books, articles, and programs designed to make the universe feel approachable. When Jupiter was first described to wide audiences, its size demanded explanation. It was too large to feel familiar as a planet, yet clearly not a star. Writers needed a bridge. The phrase failed star offered one. It suggested that Jupiter belonged near the world of stars, but had stopped just short of crossing the line. In a single phrase, it delivered scale, mystery, and a sense of drama. It worked because it felt intuitive. Space rarely gives us simple answers. The term persisted because it matched how humans naturally think. We are drawn to stories of near transformation, almost becoming something else, almost reaching a threshold. We frame understanding through contrast and comparison, not through formation histories or pressure gradients. Calling Jupiter a failed star made it easier to remember, easier to explain, and easier to repeat. But ease is not the same as accuracy. From a scientific standpoint, the phrase introduces a quiet misunderstanding. It suggests that Jupiter once stood on the same path as a star and did not go far enough. That idea feels natural, but it is not supported by how Jupiter formed. Jupiter did not begin life as a star in progress. It never underwent the conditions that define stellar birth. There was no collapse toward fusion, no brief ignition, no fading of nuclear fire. Numbers whisper more than they speak. In astronomy, classification is based on origin and process, not appearance. Jupiter's formation in a protoplanetary disk places it firmly among planets. Its mass falls far below the range required for star-like behavior. These facts are not debated. They are well established and consistently reflected in scientific literature. So why does the term remain in circulation? One reason is repetition. Once a phrase becomes widespread, it takes on a life of its own. It appears in documentaries, classroom explanations, and casual conversations. Over time, familiarity replaces scrutiny. The phrase sounds authoritative because it has been heard so often. Silence is also a kind of data. Another reason is that the term satisfies curiosity quickly. It offers a neat answer to a complex question. Why is Jupiter so big? Because it almost became a star. The explanation feels complete, even though it bypasses the real physics. In this way, the phrase closes a door that science would prefer to leave open. Modern astronomy avoids this shortcut, not out of criticism, but out of clarity. Scientists describe Jupiter as a gas giant planet formed through accretion. They describe brown dwarfs separately, as objects that form like stars but lack the mass to sustain fusion. The categories are distinct and the boundaries between them are clear. When the phrase failed star appears in scientific contexts today, it is usually framed as informal or historical language. It is acknowledged as a metaphor, not as a classification. This distinction matters especially for understanding how planetary systems actually work. There is also a human side to this story. We tend to measure significance by brightness. Stars shine, planets reflect. It feels natural to assume that light represents achievement. In that framework, something large that does not shine appears incomplete. The phrase failed star reflects that bias more than it reflects astrophysics. But the universe does not reward brightness alone. Jupiter's importance comes from gravity, structure, and balance. These qualities do not announce themselves visually. They work quietly, shaping orbits and environments over immense spans of time. No metaphor of failure captures that role. As listeners late at night, we may recognize this pattern in our own lives. We often label experiences in terms of what they did not become. Careers that did not follow a certain path. Decisions that led somewhere unexpected. The label feels explanatory, but it rarely tells the whole story. Jupiter invites a different way of seeing. When we set aside the phrase failed star, we are left with something more precise and more calming. A planet that formed as a planet. A body that never aimed for fusion and never needed to. The term tells us something valuable, not about Jupiter, but about how humans explain complexity. We start with metaphor because it feels safe. Over time, we learn to let go of it, and in that letting go there is a quiet clarity. Understanding does not always arrive through dramatic language. Sometimes it comes when we allow the universe to speak in its own slow way, without forcing it into stories of success or failure, and simply listen to what the physics has been saying all along. One of the most surprising facts about Jupiter is that it gives off more heat than it receives from the Sun. This detail often catches people off guard. To a human mind, extra heat feels like a hint of hidden fire, a quiet echo of something star-like. It is easy to imagine that Jupiter is still glowing faintly from a failed ignition, cooling slowly after a missed transformation. But that image does not match the physics. Jupiter's warmth does not come from nuclear reactions. It does not come from fusion struggling to continue. It comes from something far quieter, far older, and far more common in the universe. Space rarely gives us simple answers. To understand Jupiter's internal heat, it helps to think about time and patience. When Jupiter formed, it gathered an enormous amount of material. That material carried gravitational energy. Over billions of years, the planet has been slowly releasing that energy. Not all at once, but in a steady, almost imperceptible way. As Jupiter very gradually contracts under its own gravity, potential energy is converted into heat. This process is known as gravitational contraction. It is not dramatic. It does not produce light. It does not flare or pulse. It simply continues quietly as the planet settles into a more compact state. This mechanism is called the Kelvin-Helmholtz process, and it is not unique to Jupiter. Many large planets and young stars experience it early in their lives. What matters is that this process does not require nuclear fusion. It does not signal a failed attempt at becoming a star. It is a natural outcome of being large and massive. Numbers whisper more than they speak. The amount of heat Jupiter releases is modest compared to stellar energy. It is enough to drive atmospheric motion, to fuel storms, and to maintain internal circulation. It is not enough to initiate fusion or to suggest that fusion ever occurred. The scale matters. Jupiter's energy output is planetary, not stellar. From a human perspective, heat often implies activity. We associate warmth with fire, engines, or metabolism. In everyday life, something that produces heat feels alive or powerful. In space, however, heat has many sources, and not all of them point towards stars. Silence is also a kind of data. If Jupiter had ever undergone nuclear reactions, even briefly, traces of that history would remain. its internal structure would tell a different story. Its energy profile would reflect a past phase of fusion. Scientists see none of that. Instead, they see a planet whose heat budget aligns perfectly with slow contraction and residual formation energy. Calling Jupiter a cooling star is tempting because it fits a familiar narrative. But familiarity does not equal accuracy. Jupiter is not cooling down from a stellar state. It is slowly releasing energy it has carried since its formation, like a stone that remains warm long after sunset. There is also a human tendency to equate brightness with importance. Stars shine, so they feel central. Planets do not shine, so they feel secondary. Jupiter challenges that intuition. It is warm, dynamic, and influential without ever producing light of its own. Its internal heat drives powerful winds and long-lived storms. It shapes cloud layers that move at different speeds. It fuels an atmosphere that never truly rests. None of this requires fusion. None of it points to a missed stellar destiny. For listeners late at night, this distinction can feel grounding. Jupiter's warmth is not the result of something going wrong. It is the result of something proceeding exactly as expected. Physics unfolding patiently, without spectacle. In many ways, Jupiter's internal heat is a reminder that energy does not always announce itself. Some forms of power work best when they are quiet, steady, and long-lasting. Jupiter has been releasing heat for billions of years, and it will continue to do so for billions more, without ever crossing into the realm of stars. When we slow down and let go of dramatic interpretations, Jupiter's nature becomes simpler and more complete. It is not a star that faded. It is a planet that remains warm, and perhaps there is something calming in that realization. A body that does not burn, does not flare, and does not rush toward brilliance, yet still carries enough warmth to shape its world, reminding us that not all lasting energy comes from fire, and not all significance needs to shine. Deep beneath Jupiter's visible clouds lies a region that feels almost unreal, even by cosmic standards. It is not a place of fire or fusion. It is not a stellar core. It is a planetary interior shaped by pressure so intense that familiar matter begins to behave in unfamiliar ways. Here, hydrogen changes. Near the surface, hydrogen behaves as we expect. It is a gas, light and simple, drifting through Jupiter's thick atmosphere. As we move deeper, gravity presses harder. Layer by layer, the weight above increases. Temperatures rise, but pressure rises faster. Eventually, hydrogen is forced into a state it never reaches on Earth under natural conditions. It becomes liquid metallic hydrogen. Space rarely gives us simple answers. This transformation is not driven by heat alone. It is driven by pressure. Immense pressure squeezes hydrogen atoms so closely together that their electrons begin to move freely. In this state, hydrogen conducts electricity like a metal. It flows, it carries charge. It behaves less like a gas and more like a vast moving ocean of conductive material. This is not a sign of a hidden star. It is a consequence of being very large and very dense. Numbers whisper more than they speak. The pressures required for this transformation are millions of times greater than atmospheric pressure on Earth. No furnace is needed, no ignition, just gravity doing what gravity does slowly and relentlessly. The deeper you go, the more matter presses inward, and matter responds by changing its rules. Liquid metallic hydrogen is one of the defining features of gas giant planets. It does not appear in rocky worlds. It does not require nuclear reactions. It forms when a planet gathers enough mass to compress light elements into new states. Jupiter reached that threshold naturally, through growth, not through collapse. This conductive layer is not still, it moves. As Jupiter rotates, this vast sea of liquid metallic hydrogen flows and circulates. moving conductive material inside a rotating body generates magnetic fields. This is the quiet engine behind Jupiter's magnetism. Silence is also a kind of data. Jupiter's magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space. It traps charged particles. It shapes radiation belts. It interacts with Jupiter's moons in complex and subtle ways. None of this requires light. None of it requires fusion. The strength of the field comes from motion, not brightness, from depth, not flame. From a human perspective, magnetism often feels abstract. We cannot see it directly. We infer it from its effects. Compasses align, instruments respond. Auroras appear far from the source. Jupiter's magnetism is similar, but on a planetary scale. It works quietly, continuously, without calling attention to itself. This is where Jupiter's story diverges most clearly from that of stars. Stars generate their power at the core through nuclear fusion. Their defining feature is light. Their energy radiates outward, visible across vast distances. Jupiter's defining power moves inward. It stays hidden beneath thousands of kilometers of atmosphere. It does not illuminate space. It shapes space through force instead. This difference matters. Liquid metallic hydrogen does not indicate a star that failed to ignite. It indicates a planet that grew large enough to access deeper physical regimes. The processes at work are planetary, not stellar. They depend on pressure and rotation, not fusion and radiation. Many gas giants beyond our solar system are expected to contain similar layers. Jupiter is not unique in this respect. It is simply close enough for us to study in detail. Its interior offers a glimpse into what happens when size alone reshapes matter. There is something quietly humbling about this. Jupiter's greatest power comes from a region we will never see directly. No telescope can observe liquid metallic hydrogen. We know it exists because the physics demands it, because the magnetic field requires it, because the numbers leave no alternative. Silence is also a kind of data. For listeners late at night, this idea can resonate on a human level. We often associate strength with visibility, with display, with being noticed. Jupiter reminds us that some of the most influential forces operate far below the surface, unseen and unacknowledged. Its magnetic field protects and organizes its environment. It shapes interactions with moons. It defines regions of space where particles move and where they cannot. All of this happens without light, without heat that reaches outward, without spectacle. Jupiter does not need to shine to be powerful. In the deeper layers, the planet continues to rotate, continues to conduct, continues to generate force. This process has been ongoing for billions of years and will continue long after surface storms change and fade. It is steady, it is reliable, it is quiet. When we consider liquid metallic hydrogen, we see Jupiter not as a near star, but as something complete in its own category. A world whose depth matters more than its brightness. A planet whose influence comes from structure rather than flame. As we let this understanding settle, the universe begins to feel less like a competition for light and more like a balance of hidden processes. Jupiter stands as an example of strength without spectacle, of power that does not announce itself, and perhaps that is the calmest realization of all. That beneath layers of cloud and time, beneath expectations and labels, there exists a form of stability that does not need to be seen to endure, quietly shaping its surroundings, resting in its depth, exactly as it is. Jupiter's importance has never depended on light. It does not glow. It does not warm the solar system with radiation. It does not mark the passage of time the way the sun does. And yet, without Jupiter, the structure we quietly rely on would look very different. Jupiter's role is gravitational. From a distance, gravity feels abstract. We cannot see it, and we rarely notice it unless something moves unexpectedly. But gravity is the architecture of planetary systems. It is what holds patterns in place long after motion begins. In this sense, Jupiter is not a performer at the center of the stage. It is part of the structure beneath it. Space rarely gives us simple answers. Jupiter's mass shapes the solar system on a scale that no other planet approaches. Its gravity influences the paths of objects far beyond its visible presence. Orbits bend gently. Populations of small bodies gather, disperse, and reorganize over long periods of time. None of this requires brightness. None of it announces itself. The effect is subtle but persistent. Jupiter helps stabilize orbital relationships across the system. Its gravitational pull acts as a long-term regulator, reducing chaos rather than creating it. Objects that might otherwise drift into unpredictable paths are guided into patterns that repeat, quietly and reliably. This is not a single, dramatic event. It is a continuous process unfolding over millions and billions of years. Numbers whisper more than they speak. When scientists model planetary systems, Jupiter's influence becomes clear. Remove it, and the simulations grow noisier. Orbits shift more erratically. Small changes accumulate faster. Stability becomes harder to maintain. Jupiter's presence does not freeze the system, but it dampens extremes, allowing long-term order to emerge. This kind of influence is easy to overlook because it does not produce spectacle. There are no flares or sudden transitions. The work is done slowly, through gravity acting at a distance, reshaping motion one small adjustment at a time. Silence is also a kind of data. For humans, this idea can feel counterintuitive. We often equate importance with visibility. We notice what shines, what moves quickly, what demands attention. Jupiter asks for none of that. Its influence is felt precisely because it does not change rapidly. Stability requires patience. Over time, this stability has shaped the environment in which the inner planets exist. It has influenced the distribution of debris. It has affected how material moves through the system. While Jupiter is not a shield in a simple sense, its gravitational role has contributed to a calmer, more predictable neighborhood closer to the Sun. This does not mean Jupiter controls everything. The solar system is not rigid, it evolves, but Jupiter provides a steady gravitational background, a kind of rhythm that other bodies move within. Like a slow, deep note beneath a melody, it is not always heard, but it defines the harmony. There is a human parallel here. In families, in communities, in systems we depend on, the most stabilizing forces are often the least visible. They do not seek attention. They create space for others to move safely. Jupiter occupies a similar role on a cosmic scale. It is tempting to imagine that if Jupiter had become a star, its influence would have been greater, brighter, more obvious. But brightness is not always compatible with stability. A second shining source would have altered temperatures, radiation levels, and orbital dynamics in ways that could have disrupted the delicate conditions required for long-term order. Jupiter did not need to shine because shining was not its function. Its power lies in mass, not light, in presence, not display. It shapes trajectories rather than illuminating them. It works through constraint rather than forceful intervention. Silence is also a kind of data. When we study planetary systems beyond our own, we see variations on this theme. Large planets often play similar roles, anchoring structures, influencing motion, and creating long-term patterns without ever becoming luminous. Jupiter is not an anomaly. It is an example of how systems organize themselves efficiently. Late at night, when the idea of influence without visibility begins to settle, Jupiter's role feels less technical and more intuitive. It reminds us that not all contributions are loud, not all support is seen. Some forms of order exist precisely because they remain in the background. Jupiter has spent billions of years doing exactly this, holding space, shaping motion, allowing complexity to unfold without drawing attention to itself. It never needed to shine to matter, and perhaps that is the quiet lesson of its presence, that stability does not announce itself. That order often emerges from forces we do not notice, and that in a universe full of light, there is room for something just as important to exist in shadow, shaping the environment gently, continuously, and without ever needing to be seen. It is natural to wonder what might have happened if Jupiter had crossed a different threshold, if it had gathered far more mass, if gravity had compressed its core until nuclear reactions began, if somewhere beyond the Sun, a second source of light had quietly turned on. The image is intriguing. But when we follow it carefully, the calm of the solar system begins to fade. A system with two stars is not inherently unstable, but it is very different. Two sources of energy reshape everything around them. Light, heat, and radiation no longer arrive from a single direction. Orbits become more complex. Balance becomes harder to maintain. Space rarely gives us simple answers. If Jupiter had become a star, even a small one, the solar system would not be the quiet place we know. The steady rhythm set by the Sun would be joined by another influence, one that changes how energy is distributed across space. Temperatures would shift. Radiation levels would rise. Long-established patterns would be rewritten. Numbers whisper more than they speak. Even modest stellar output would matter. Jupiter's position far from the Sun might suggest safety, but light travels easily. Over long periods, even small changes accumulate. The outer regions of the system would warm. The inner regions would experience subtle but persistent shifts. Stability would become more difficult to sustain. One of the most important consequences would be orbital complexity. With two massive luminous bodies, gravitational interactions grow more intricate. Paths that are smooth and predictable in a single star system become sensitive to small disturbances. Minor deviations can grow over time. The calm repetition that allows environments to remain stable becomes less reliable. Silence is also a kind of data. When scientists study systems beyond our own, they find that stable, life-friendly arrangements are more common around single stars. This is not because multiple star systems cannot exist peacefully, but because simplicity favors long-term consistency. One source of energy is easier to adapt to than two. Life, as we understand it, depends on balance. It requires temperatures that remain within narrow ranges for very long periods. It requires radiation levels that do not fluctuate dramatically. It requires environments that change slowly enough for complex systems to adjust. A second star would challenge all of this. Human experience offers a quiet analogy. In our own lives, stability often comes from consistency rather than intensity. One steady source of support is easier to rely on than two competing ones. The presence of more energy does not always create better conditions. Sometimes it creates noise. Jupiter becoming a star would also change its role as a gravitational anchor. Instead of shaping the system through mass alone, it would introduce energetic feedback, radiation pressure, stellar winds, effects that push outward rather than gently guiding motion. The character of the solar system would shift from calm structure to ongoing adjustment. This is why the idea of Jupiter as a star feels less like a missed opportunity and more like a disruption avoided. Silence is also a kind of data. By remaining a planet, Jupiter contributes stability without adding complexity. It shapes orbits without flooding space with energy. It influences motion without overwhelming delicate balances. This combination turns out to be rare and valuable. The absence of a second star allowed the solar system to remain quiet enough for long processes to unfold. It allowed planets to settle into predictable paths. It allowed conditions on Earth to remain stable long enough for life to appear, adapt, and persist. The most important outcome of Jupiter not becoming a star may be what never happened. No excess radiation, no competing gravitational centers, no long-term instability that slowly erodes the possibility of complexity. In this light, Jupiter's nature feels intentional, even though intention does not exist in physics. It occupies a role that supports rather than challenges, that restrains rather than disrupts. Numbers whisper more than they speak. When we step back, the idea becomes clear. The solar system did not need another light. It needed balance. It needed a massive presence that could shape structure without adding noise. Jupiter provided exactly that. As we let this thought settle, the question changes. Instead of asking why Jupiter failed to become a star, we begin to see why it was essential that it did not. Some possibilities are best left unrealized. Some thresholds are better not crossed. And perhaps that is the quiet lesson of this imagined alternate history. That absence can be as important as presence. That restraint can shape outcomes more gently than force. And that in a universe where light is abundant, it is sometimes the things that do not shine that make life possible, simply by staying exactly where they are. Not every object in the universe needs to reach an extreme. Some reach completion by stopping exactly where they are. Jupiter is one of those objects. From the outside, it may appear unfinished to an impatient observer. It does not shine. It does not burn. It does not cross the dramatic thresholds that turn gas into fire. But when we step back and view Jupiter within the larger structure of the solar system, a different picture emerges, one that feels quiet, balanced, and complete. Space rarely gives us simple answers. In astronomy, progress is not defined by intensity. It is defined by stability. Stars push toward extremes of heat and pressure because their formation demands it. Planets do something else. They grow until conditions tell them to stop. Jupiter listened to those conditions. It gathered mass until the surrounding disk thinned. It accumulated gravity without collapsing inward. It became large enough to matter, but not so large that it disrupted everything around it. That stopping point was not accidental. In the universe, many roles exist precisely because something did not continue growing. Asteroid belts exist because planets did not form there. Moons exist because material settled into orbit instead of merging completely. Stability often comes from limits, not from excess. Silence is also a kind of data. Jupiter's story fits this pattern perfectly. It did not pause mid-transformation. It completed the transformation it was undergoing. A gas giant formed through accumulation, layered structure, internal heat, and gravitational influence. Nothing in its history suggests interruption. Nothing indicates abandonment. From a human point of view, this idea can feel unfamiliar. We often measure worth by how far something goes, how much it expands, how brightly it shines. But the universe measures differently. It values balance. It rewards configurations that can endure. Numbers whisper more than they speak. When scientists look at Jupiter's mass, orbit, and internal structure, they see coherence. Each property aligns with the others. There is no mismatch between scale and function, no excess energy looking for an outlet, no instability waiting to unfold. Jupiter is not a near miss, it is a resolved outcome. There is also a human comfort in recognizing this. Many of us carry quiet questions about paths not taken. about versions of ourselves that might have gone further, burned brighter, or reached different extremes. Jupiter offers a different perspective. It shows that stopping at the right point is not a failure, it is a form of precision. By remaining a planet, Jupiter supports the solar system without overwhelming it. Its gravity shapes structure, its mass provides stability, its presence allows long-term patterns to persist. None of this requires it to become something else. This completeness is subtle. It does not announce itself. It reveals itself only when we consider the system as a whole. Silence is also a kind of data. In a way, Jupiter reminds us that fulfillment does not always involve crossing thresholds. Sometimes it involves recognizing when a process has reached its natural conclusion, when growth has done its work, when balance has been achieved. Jupiter did not stop too soon. It did not stop too late. It stopped exactly where the conditions placed it. That is not incompletion, that is alignment. As this understanding settles, the language of failure quietly falls away. What remains is a planet that fits its environment with remarkable precision, a presence that supports without demanding attention, a form that does not need to justify itself by becoming anything more. And perhaps that is the calmest thought to carry forward, that in a universe shaped by limits and thresholds, there are moments when the most meaningful outcome is not to push further, but to arrive fully where you are and remain there, steady and complete, letting the rest of the system unfold around you in its own quiet time. We began with a simple idea. Jupiter was never a failed star because it was never a star that was trying. As the story settles, that distinction becomes clearer and gentler. Jupiter did not pause on the edge of transformation. It did not miss a final step. It followed its own physical path from the very beginning, one shaped by mass, distance, and time. The label of failure dissolves when we see that there was never an attempt to become something else. Space rarely gives us simple answers. In the universe, there are no expectations to meet, no unfinished ambitions, no goals waiting to be fulfilled. There are only balances that form and persist. Jupiter exists within one of those balances. It does not burn because it does not need to. It does not shine because its role does not require light. Failure is a human word. The universe does not use it. What remains is an image that asks for no interpretation. A vast body of gas, turning slowly in the dark. No glow, no regret. Just motion held steady by gravity. Just presence held in the right place. Silence is also a kind of data. Jupiter's quiet existence supports the structure around it. Its mass shapes paths. Its gravity keeps patterns from unraveling. It contributes without announcing itself. This is not absence. It is restraint. As we prepare to rest, this thought can feel reassuring. While we drift into sleep, Jupiter remains exactly where it has always been. Moving slowly, holding steady, not striving to become anything more than it already is. Numbers whisper more than they speak. The solar system continues its rhythm because each part stays within its role. Jupiter does not compete with the Sun. It does not challenge the balance. By remaining a planet, it allows everything else to remain calm. When our thoughts fade and the night deepens, Jupiter is still there, unlit, unhurried, complete. And in that quiet completeness, it keeps the larger system at ease. Perhaps that is enough, not becoming something else, not crossing every threshold, simply being where you belong, and letting the rest of the universe remain peaceful because of it.